And what could you do with these? To do that, I have to recall to start by a brief history of the measurement of time. And you will see all the progress which have been made during the centuries. In the 14th century, the time was measured by tower clocks. You had a thing called a foliot, which was suspended on a thread, and by torsion, it was going back and forth, and a dented wheel was used to count the period. And this was a very primitive clock. In the 17th century, and we find again our heroes, Galileo and Huygens, developed the pendulum clock, which was based on the oscillation of a pendulum, and there are very complicated, very ingenious escape mechanism to count and to translate this into the motion of a needle, of a hand on a dial. Then in the 18th century, the system was miniaturized, and it was the oscillation of a spring. This was the marine chronometer developed by Harrison and Hooke, and this was a big progress because the clock was small and it was more precise. Then in the 20th century, quartz clocks were developed. It was the oscillation of a fork made of quartz, and this oscillation was translated into an electrical oscillation through the piezoelectric effect. The principle is always the same. You need an oscillator, which gives a given period, and it has to be coupled to an escape device which counts the period. And of course, the higher the frequencies, the more difficult is the escape because you have to count higher and higher frequencies. What about the relative uncertainty? The tower clock had an uncertainty of 10⁻². That is 1 part in 100. That is about a quarter of an hour per day. That was the best you could do with that. The pendulum clocks had an uncertainty of a few seconds per day, at best. Harrison's clock had a precision of about 1 second per month, which was important because you could carry this clock on a ship and compare the local time with the time in London or in Greenwich and measure the longitude in this way. So it was a primitive GPS, and you saw the GPS is always based on the measurement of time. And then the piezo clocks gave 1 second per year, and I remember when I had my my quartz clock in the 1960s, I was amazed by the fact that you can keep the time within a precision of 1 second per month or 1 second per year. But what I want to say is that these 6 orders of magnitude, which were obtained during 6 centuries, are nothing compared to the 10 orders of magnitude that we have gained since the 1960s. And this is due to, in particular, to the lasers. So what are the elements that you need to make an escape mechanism? I have shown you here a laser which oscillates on 5 modes. In order to oscillate, the laser should have satisfy boundary conditions. The field should have an integer number of wavelengths between the mirrors. So you see here a very simple example. We have 5 modes which escape from the laser. But of course, you have to make the sum of these modes. And if they are in phase, you get as a sum a pulse of light. And of course, this repeats. So you have mode-locked lasers, which have several modes beating with each other, give rise in the time domain to bursts of light, periodically spaced bursts of light. And they are very well periodically spaced. The time difference between 2 pulses is inversely proportional to the frequency difference between 2 modes. And this gives rise to a very, very stable source of radiation. Here I have represented 5 modes, and you can have maybe in a laser 1,000 modes. But you can do much better if you have this light going through a fiber, a special fiber which is structured, which has a lot of holes in it. By nonlinear effects, the modes start to interact with each other, and it gives rise to a spectrum. It widens, it broadens the light spectrum, and you see when the light is coming out, you have a spectrum which gives basically white light going from the red to the blue. It looks continuous, but if you look with high enough precision, what you find is that this light is in fact made of equally spaced modes, very regularly spaced by a few gigahertz. This is called a frequency comb. And this frequency comb is the ideal escape mechanism for an optical clock. In fact, what you do is the following. You have a very stable laser. You divide this laser beam in 2 parts. One part is going to the atom, which is the reference in frequency, and you lock the laser so that it is exactly at the frequency required to excite the atom from one level to the other. Then the second part is sent to a frequency comb, and you lock the frequency comb to this laser beam. And now you have a frequency source whose frequency is perfectly measurable. You can count the frequency by looking at the teeth of this frequency comb. So a laser comb locked to optical atomic transition acts as a clock escape mechanism. And there are two competing systems now. One is to lock this frequency comb to a single ion in a trap. This is Dave Wineland experiment. And the other one is to lock the frequency comb to an ensemble of cold atoms which are kept by optical tweezers at well-defined places in space. And the uncertainty becomes 10 minus 17, 10 minus 18. 10 minus 18 is 1 second in the age of the universe. So you see, you take 1 second. You take 10 minus 18 of a second, you can achieve it with attosecond pulses. And 10 to the 18th second is the age of the universe. So if you look at 1 second, it is logarithmically just in between the age of the universe and the shortest pulse you can achieve. So what is 1 second in the age of the universe? Just take two clocks like this one and displace one with respect to the other by 30 centimeters. The time that the clocks would indicate changes because of general relativity. General relativity tells you that the time at which a clock is ticking depends upon the intensity of the gravitational field where you are. In fact, you see this effect if you put a clock on a satellite because it's very far. But now you have the sensitivity which tells you at which altitude you are within less than a meter. It means that if you move the clock on the ground and if you have inside the Earth some fluctuation of density related, for instance, to the existence of some metals or some objects which are very heavy, you can see that just by measuring the time.